Hello, hello. Here we go, folks. 213-214. Now, this is a very heavy context question. I ended up getting D, and let me explain if that wasn't your answer there. And this one's pretty straightforward type of a raffle question. So let's take a look at both of these. It says, when using a one-sample T procedure to construct a confidence interval. So we can totally construct a T procedure confidence interval for mean from a finite population. So we talk about that all the time. We can have a finite population. And again, we know that the conditions met are R and I. And these conditions are met because mathematically the numbers might be off if we're not following these conditions. It states the condition is that the sample size has to be at least the population size has to be at least 10 times the sample size. And more times than not, this is always the case. The reason for this condition is to ensure independence. So R, we've seen a couple different times. We have to have a random design. That absolutely has to be there. The number has to be high enough for it to approach normality, and we're using T to approximate information we know about normal curves. And the I is this test. The population size must be at least 10 times the sample size. And so let's figure out what this means by, well, how would that make it not independent? So let's think for a moment about a deck of cards. If we were to play cards, there's 52 cards. So one card game you could play is 52 card pickup. So we know that out of all the hearts in the deck, a quarter of them are hearts. So we could do a little math and figure out, okay, a quarter of them, because there's 4 different suits in a deck of cards. So if I multiplied that, I would get 13 hearts in a deck. So my chances of picking a heart is 13 out of 52. Well, let's imagine that the 52 were just a simulation, and that was my population. Notice if I do end up picking a heart, if I end up selecting a heart, when I go to do more samples, let's say I want to do a sample size of 10, and notice the number 52 is not 10 times larger than 10, and so we're going to have a problem with independence, and I'm going to show you why. If you end up picking a heart and you don't replace, if you don't put replacement built into your study, then notice now if you did end up picking a heart, now there's only 51 cards and only 12 of them are hearts. So 12 out of 51 is not 0.25 anymore, it's 0.235. And so notice that without replacement, you didn't have an equal chance of getting a heart. You did not have a 1 in 4 chance of getting a heart without replacement. And so that's what drives us to want to put this test, a test for independence. We want to do 10 times N as to be a minimum size for our population. Okay? So let's show that. I'm going to show that. Imagine I do a same card game, but I use 12 decks. So I'm going to make my population a lot bigger. If I use 12 decks of cards, then that would in essence be 624 cards. And so 25% of those, or that'd be 156 hearts out of 624. And you can check my math. If I divide those two numbers, you get 0.25. And that's the probability of getting a heart. Let's say once again, same design, but now I have 624 in my population because I have 12 decks of cards. Let's say I do end up picking a heart. So there's one less heart in the deck. And of course, I picked a heart and I didn't replace. So this is without replacement. If you do the math here, because this number is so big, once again, you pretty much get, still, because there's so many decks of cards, you still get the same probability. So with or without replacement, the probability is independent. It's basically 25% of the time you're going to pick a heart, even if you didn't replace, because the population is large. That's what this question's stating. Now let's look at question 214. It says you're running a raffle. You sold 1,000 tickets. Notice this expected value. So you can create a table, and notice I sold 1,000 tickets and we decided only one ticket was the winner. So that means out of 999 people, they're going to lose their $1 bill and not get anything else back. And one guy is going to win, in essence, $49. Now, the reason why he won't win a full $50 is because, remember, he paid for his ticket price. So this is merely $50 minus the $1 he spent for the ticket. You got to pay to play. So now, if I was running this, and let's say this was my fundraiser, I'm going to get an expected value, this times this plus this times this, 999 $9.99 plus 49. Notice as a whole, this is not what I'm collecting. Anytime I collect a ticket, that's plus to me, but they want to know the expected value for each ticket. Okay, so I'm doing that. Negative 999 plus a 49 would give me 950. So in essence, I'm going to make 950, and all these 1,000 people are going to lose a grand total of $950, which makes sense. I sold 1,000 tickets for $1, but I paid out $50. Well, on average, remember, if you divided that by 1,000 people, on average, they're losing 95 cents. And that's, in fact, what it's saying here. So a ticket owner, on average, loses 95 cents. Really, all 999 lose the full dollar, but one guy wins $49. And so on average, out of the 1,000 people, they all lose a grand total of $950. So that's an average of 95 cents per person. Thanks again for joining us.